Hello, folks. It's Professor Fiore. Today, we're going to talk about decibels. Certainly a term you've heard before. Lots of people use this term. Maybe they don't quite understand what it really means. What the heck is a decibel? Well, it's really nothing more than a ratio. A decibel is a ratio expressed in base 10 logs. That's really all it is. Now, the base unit is really called a bell after Alexander Graham Bell. Turns out a bell is a little bit too big of a number. It's kind of like trying to measure your weight in tons. You know, you always have a fraction basically. So we use a decibel. Deci is 1/10. So a decibel is literally 1/10 of a bell. Now, there's a couple different ways we can do a computation. If we're talking about powers, for example, the power out of an audio amplifier feeding a loudspeaker, what we would do is we would say the dB value, little d, big B, right, the dB value is going to be 10 times, because that's the deci part, 10 times the log base 10 of the ratio of two pressures. So I will say power 1 and power 2. Right, so it's a ratio of two things. Now, if we were talking about like an audio amplifier, a power amplifier, power 1 would be the output power, the power going to the loudspeaker. Power 2 would be the signal input power. Not to be confused with the power coming in from the AC mains, but the signal input power, right? So I would say this amplifier has a power gain of 100 or something. I put in 1/10 of a watt, I get 100 times that, 0.1 times 100, 10 watts going to my loudspeaker. Right? So that's all that is. It's just a ratio of these two things. So we would take the log base 10 of that, you could use a little calculator, right? And then multiply that by 10, we have a value in decibels. That simple, okay? It's really that simple. Couple of round figures you can use to make your life easy without always having to reach for a calculator. Factors of 2 are approximately 3 decibels. It's 3.01 and some change, but we just basically say it's about 3 dB, okay? Factors of 10, because this is base 10 log, factors of 10 will turn into 10 dB. Now, because you're using a log, logs reduce the strength of a computation. In other words, if you were doing a multiply, it turns into an add when the values are in logs. If you're doing a power, that turns into a multiply. So if you're going to add and subtract in dB, that's equivalent to multiplying and dividing in ordinary form. So just to take a real quick example, all right? Let's say we have a ratio of 8, right? I don't really care what the actual powers are. I mean, it could be 8 watts and 1 watt. It could be 8 milliwatts and 1 milliwatt. It could be 16 watts and 2 watts. Just 8, right? It's the ratio of 8 because dB is all about ratios, ratios. So I say, okay, what's 8 in terms of factors of 2 or factors of 10? Well, I could say that's equivalent to 2 times 2 times 2, right? 2 times 2 is 4 times 2 is 8. So what I do is each of these factors of 2 turn into 3 decibels, and each of these multiplies turns into an add, right? Again, logs reduce the strength of the computation. Multiplies turns into adds, divides turns into a subtraction, and so forth. So this becomes 3 dB plus 3 dB plus 3 dB, right? Each factor of 2 turns into 3 dB. Each multiply turns into an add. So it's 3 plus 3 plus 3. So a factor of 8 is equivalent to 9 decibels. In other words, we would say that the output in my power amplifier, for example, we would say the output is 9 decibels greater than the input. Okay, that's really all it is. Now, there is a little bit of a variation on this, which deals with, instead of powers, something other than power, like pressure, right? When we talk about sound, we're interested in sound pressure levels. So there's a little bit of a difference here. In electrical circuitry, we might be talking about, instead of a power gain, we might be talking about a voltage gain. That's very typical. Well, power will vary in accordance with the square of voltage. If you double a voltage, keeping everything else the same. If you double a voltage, the power doesn't go up by a factor of 2. It goes up by 2 squared. 4, right? So I don't want to have to create like a different version of this for, powers and volts. Sound pressure is similar to voltage. Matter of fact, voltage is often referred to as electrical pressure. So those two things fall into the same kind of category, right? So I don't want to have to come up with 2 different versions of this. So what we do is we just think, okay, well, if the pressure and the power are related through a power of 2, a squaring, right? Voltage squared is power. The acoustic pressure squared, same sort of deal. That squaring, right, that's an exponent. So again, we reduce the computation strength using logs. That exponent turns into a multiply. So squaring something, once you put it in logs, is like multiplying by 2. So if I have, instead of powers, if we have pressures, all we have to do is modify this equation by a factor of 2. So my dB in that case would be 20 times log base 10. Oops. Clean that up a little bit. Instead of power 1 over power 2, it's pressure 1 over pressure 2. So like I said, if you were doing this with voltages, just remember voltage is analogous, right? It's electrical pressure. But, we're kind of focused here on looking at what's going on with sound, right? Sound pressure levels. Okay, so in this case, because there's a factor of 2, our doublings turn into 6 dB, and our decades, our factors of 10, will turn into 20 dB. Okay? Now, if something goes down instead of increasing, right, because I was talking before, like a power amplifier, you say the output is 8 times, 50 times, whatever it is, bigger, things could have loss, we have less, so what ends up happening there? Well, we end up with negative values. It's still, factors of 2 are 6 dB, factors of 10 are 20 dB, or 3 and 10 if you're doing the power version. But if things are getting smaller, then they just become negatives. So a factor of 2, 1/2 is a factor of 2 going the other way, right? 1/10 is a factor of 10 going the other way. So those would actually show up as like, negative 6 dB, negative 20 dB. A thing to remember is that unity, 1, right, turns into 0 dB. If there's no change, that's 0 dB, right? 0, none, there's no change. So if I ever come up with a dB value that's positive, I know there's an increase in signal. If I come up with a dB value that's negative, then I know there's a decrease in signal, right? Fairly straightforward in that regard. Okay, so we could do a quick example here, right? Using the pressure version. So let's say I have an increase in a factor of 40. Maybe the sound pressure level has gone up by a factor of 40. Maybe I've got an amplifier, with a voltage. The voltage has gone up by a factor of 40, right? Either one of those. So my factor of 40, right? I can write the factor of 40 as 2 times 2 times 10. Of course, you can always just get out your calculator. You got a scientific calculator. You could just, plug in 40, take the base 10 log of it, multiply by 20, you got your answer. But just trying to give you some little, quickie things here you can kind of do in your head, get some ballpark numbers. That's a really handy facility to develop. Anyway, so 40 you can think of as 2 times 2 times 10, right? 2 times 2, 4 times 10, 40. Okay, so take each one of these factors of 2, because we're doing a pressure version now, right? We're doing a pressure version now. So each one of these factors of 2 turns into 6 decibels. And the multiplies all turn into adds. Right? The factor of 10 turns into 20 dB. Right? So we got 6 and 6 and 20, right? 32 dB. Beautiful. Okay? All right. Now, we're just really talking about, these two sort of random things, right? 2 powers, 2 pressures. We can come up with standards. We can come up with references. Now, there's a lot of references, when we start talking about, electrical systems. There are different standards for things like dBW and dBm and dBf and all of these different kinds of things. In sound, we're primarily interested in sound pressure level, what is called dBSPL, right? SPL, sound pressure level. So sound pressure level, we need a reference, right? That power 2, or in this case, the pressure 2, the thing in the denominator. We need a reference for that. All right, so our reference, in other words, what we're going to call 0 dBSPL, any negative value is something so quiet you can't hear it as a human. All right, so 0 dBSPL, that reference is going to be 20 micropascals. All right, remember, Pascal is the metric unit for pressure. If you're used to using, U.S. customary units, you might be thinking in terms of PSI, pounds per square inch. A Pascal is really small compared to pounds per square inch. There's a factor of roughly 7,000 between them. So 7,000 Pascal will give you like 1 pound, 1 pound per square inch. Okay, so it's a very fine unit. So 20 micropascal is what we refer to as the threshold of hearing. We do that, and this is something you're going to see over and over again. We use a reference frequency typically of 1 kilohertz. All right, so the frequency associated, we say, okay, it's 1 kilohertz. It's pretty much in the sort of upper mid-range maybe. It's not into the treble yet. But it's kind of an irritating tone if you just listen to a 1 kilohertz test tone. Anyway, so we say that this 20 micropascals is right about the threshold of hearing at this 1 kilohertz tone. Right? If we go considerably lower than that, you can't hear it. Humans can't hear it. Maybe other animals can, but humans can't. And as we go above that, 100 pascals, 500, whatever the heck it's going to be, 500 millipascals, whatever it works out to. We're talking about increasing sound pressure levels, right? Again, it's pressure. So if I went up to 40 micropascals, if I double it, right? Think of that equation that I just erased a moment ago. That's a factor of 2. It's pressure, so that's 6 decibels. So 40 micropascal would be 6 decibels above my reference. My reference is literally 0 dBSPL, so we would refer to that as 6 dBSPL. Right? 6 dB by itself is just a ratio. 6 dBSPL is a specific pressure level. Whenever you add one of these things to the end, dB something, the something is always referring to a reference, so it's an absolute value. Right? If I was talking like a power amplifier and I said, this thing has a gain of 20 decibels, it doesn't really tell me what the level is. It just says it's 20 decibels hotter. It's 20 decibels bigger than the input. Okay? On the other hand, if I had, one of these extra references, and a typical one in that case might be dBW, where the reference is 1 watt, you'd say, well, it's 20 dB bigger than the reference of 1 watt. That's a specific power level we could talk about in watts. We can do that with voltage. We can do that, obviously we can do that with sound pressure levels, with pascals. All right? Okay, So just to put maybe a finer note on this, no pun intended, 1 Pascal. Okay, that's a pretty small value. Remember, it's going to take 7,000 Pascal to get you 1 pound per square inch. Standard pressure, right? Atmospheric pressure on Earth at sea level is roughly 14.7 pounds per square inch. So, 1 Pascal, okay? Pretty tiny in comparison to PSI. So this is like 1/7,000th of a PSI, basically, right? What does that turn into as far as dBSPL? What's the factor, all right? Well, how many times bigger is 1 than 20,000? You can just get out the formula, right? You can say, oh, well, my dB value, in this case, my dBSPL value, is just 20 times log 10 of, excuse me, the pressure I'm interested, the 1 Pascal, over my reference, right? My reference for SPL is 20 micropascals. What does that work out to? Well, that's this. Like I said, you could just get your calculator and crunch through this, but you could actually do this in your head fairly quickly. 1 Pascal over 20 micropascals. That's a factor of 50,000, right? You got to multiply this by 50,000 to get 1 Pascal. So I've got a factor of 50,000. 50,000 times. Well, let me think about that in terms of factors of 2 and factors of 10. I can use my 6 dB as a factor of 2 and my 20 dB as a factor of 10, right? So what is that? Well, you could think, well, it's 5, times 10, times 10, times 10, times 10. The quick way to think about this is that it's 1/2 or 0.5 times 10 to the 5th. In other words, 10 times 10 times 10 times 10 times 10. Okay. Well, 1/2, that's a factor of 2. It's just the reciprocal. Remember, reciprocal, when you're going down, you're getting smaller. It's negative dB. So this turns into minus 6 dB. All these multiplies, of course, turn into adds. Each of these tens, factors of 10, turn into 20 dB. All right, so I've got 5 of them. Let's squeeze it out of the board here. All right, 20, 20, 20, 20, 20. It's 100 minus 6. It's 94 dB SPL. How loud is 94 dB SPL? Well, the first thing I'm going to say is that SPL is not loudness. And we're going to take a really close look at that in the next video. What's loudness compared to SPL? They're correlated, but they're not the same thing. All right? Loudness is the human perception of sound pressure level. They're not identical, but they are correlated. But just to kind of give you a broad idea, right? 94 dB SPL is damn loud. For a normal kind of background kind of thing, this is a nice high-powered stereo that's just screaming, right? You just got this thing cranked up. If you're in the mid-90s, a conversation, right? You walk into a classroom, maybe or a party, you got some people just speaking, right? Nothing fancy going on. I don't have music going on or whatever, but just basic conversation. You might be talking 70 dB SPL, 75, all depending, somewhere in that region. When we start talking about something a little louder, like maybe a vacuum cleaner, you're going to clean the house up, we might be talking 80, okay? You start cranking this thing up higher and higher and higher. You start getting concert sound pressure levels rather than your home stereo. Things are going up considerably. You might be talking values over 100, 100, 105, 110 dB SPL. If you were a few hundred feet away from a jet taking off, that might be 130 dB SPL. Just a little side note here. In the US anyway, OSHA, right, a US federal government agency, if you work in a factory or someplace like that, and the sound pressure level, the average sound pressure level over an 8-hour day is over 90 dB SPL, it's actually a weighted thing that we'll talk about in another video, but over 90, you have to have hearing protection to protect your ears. And the higher it goes, the shorter the duration is without hearing protection. So if you're working in an area where it's 94 dB, okay, 94 dB SPL, technically it'd be dBA. Like I said, we'll talk about that. But you would have to have hearing protection if you're going to work in there for 8 hours. And as that level goes up, 94, 96, 100, 105, the time duration that's allowed without hearing protection keeps getting shorter and shorter and shorter and shorter. Until eventually you get to a point where it doesn't matter if you're going to be in that room for a minute, you're going to have hearing protection, right? To save your ears. You only get one pair. You can't trade these in and get new ones, right? So you always want to be careful about your ears, all right? Okay, so that's really all there is to talk about as far as decibels are concerned. It's just a ratio that's represented in this logarithmic form, right? So you take the base 10 log, because there's two kinds of logs, right? Common logs and base 10 logs. You take the base 10 log of the ratio, whether it's power or pressure. If it's a power ratio, you're going to multiply that by 10 because it's decibels. If it's a pressure, a voltage or a sound pressure level, power varies as the square of those quantities. So that extra factor of 2, we modify the equation so it's 20 times the log base 10 of the ratio, right? So for those kinds of things, remember the factors of 2 are 6 decibels, right? If you're going up by a factor of 2, it's plus. If you're going down by a factor of 2, it's minus. Every factor of 10 turns into 20 dB. The multiplies turn into adds, right? And that's basically what we're looking at. If we have a defined second power, in other words, if we have a reference level, as we do here, SPL, that reference level is 20 micropascals, so we're measuring everything with respect to that, right? And even extraordinarily loud values, right? 94 dB SPL is, under normal circumstances, you would say is pretty loud. That's only 1 Pascal. And to put that into everyday terms, 1 Pascal, air pressure, 14.7 pounds per square inch, that's about 101 kilopascals. So when you look at the variation in air pressure, a high pressure thing comes in, weather system comes in, low pressure, whatever, you see a little bit of variation in the air pressure, but it's something that we can't even draw here to scale, because even an excruciatingly loud sound level, right? If you get up to 110, 120 dB SPL, the variation in that sound pressure is actually smaller than the thickness of the line I'm going to use to draw the pressure curve, right? If you could fully modulate the atmosphere, you'd be looking upwards, not quite, but you'd be looking upwards of 200 dB SPL. Just blow your ears right out. It'd kill you, basically, right? Okay, so that's what we're looking at. Our next video, we're going to talk about loudness. Loudness being the human perception of sound pressure level. See you next time.